SHIP Conference. My name is David Ramirez. I'm going to be presenting today on Artificial Intelligence Special Operations, Deep Machine Learning Applications. I'm representing General Dynamics Mission Systems, whom I work for as a machine learning engineer. So here's our topics for today. Y'all came here for some machine learning, but you're going to get a mix of a couple different topics, including some of my personal perspectives. We're going to start with some of the distinctions between AI and ML. And for that, I've got a quick video I'd like to show. Next, we're going to move into some of the fundamental concepts related to different sorts of machine learning and how they work at a high level. I'd like to share a few tips about how to effectively use machine learning. Where I work, these are described as the 4 enablers of machine learning success. They're going to be some of the key milestones which help you to start a successful machine learning project. After that, we're going to change gears a little bit. We're going to talk about culture, race, bias, America and the military from some of my own personal perspectives. We're going to wrap that section up with a historical perspective on safety in the United States. Then we're going to circle back to machine learning for military applications. I'll give examples of how machine learning has been used, some scenarios which have achieved remarkable results. I'm going to frame those within the context of those 4 enablers of machine learning success. Finally, we will end with a discussion on future considerations of ML within the military and some of our ethical responsibilities as engineers in designing the AI of the future. So a little bit about me. I was born and raised, I'm a current resident of Arizona. After high school, I joined the United States Marine Corps, and I served from 2008 to 2012. I am a current student and also a graduate alumni of Arizona State University, where I received my bachelor's and master's degree in electrical engineering, and I'm currently pursuing a PhD with a focus in artificial intelligence. While going to school, I'm also a full-time engineer at General Dynamics Mission Systems, and I have been since 2017. So before we get into some technical details, I think it's important to touch on this subject, this being the SHIP conference and the year that we're in. Race is on everyone's mind, and there's been a lot of progress in confronting some of these very challenging issues. That being said, I've got a disclaimer here. We're going to talk on some personal topics that are my own viewpoint, not necessarily the viewpoint of my employer. But General Dynamics Mission Systems does have a blossoming community for multicultural expression, women's empowerment, LGBTQ, and military veterans support. So an introduction to machine learning. What is it? Well, it's a tool for problem solving. And we're going to talk about how you set up those sort of problems. But before we do, it's a little unorthodox, but I'd like everyone to check out this YouTube video. This is going to set some of the foundational knowledge which we're going to build upon related to artificial intelligence and machine learning. It's a quick video, less than 10 minutes. And if you can pause your presentation now and go check it out, this will really set the stage for the rest of my presentation. All right, time has passed. Hopefully you've watched the video. We're going to jump deeper into some slides now. So what is AI versus machine learning? Well, as you saw in that video, they talk about handcrafted AI. And this has been done for years in software. You might have a human look at a particular problem and engineer rules which attempt to solve that problem in software. It takes data inputs here on the left. It looks at what outputs you need to produce depending on the situation, and the human defines those decision rules. This is in contrast to a machine learning algorithm, which is example driven. Instead of a human defining all these intricate rules in software, instead, you give it the inputs and you give it the outputs. And the machine learning algorithm finds the connection to go from A to B without having to define anything explicitly. The way it does that is through this learning feedback. It attempts to solve the problem. It then evaluates itself because it knows the true outputs. Because it can score itself as it goes, it can get better over time in order to get the highest score on your known outputs. So this relates very heavily to supervised machine learning, which was one of the 3 types discussed in the video. In supervised machine learning, we're given inputs. They could be images, perhaps of cats and dogs. We're also given the labels that we want to try to predict. Those being either cats or dogs, some other type of image level label. The algorithm attempts to go from A to B with these learned decision rules. So because we know what the output should be while we're developing, while we're training this algorithm, it scores itself with this feedback loop, and we're able to create a solution which attempts to minimize the error in this output. This output might be image level labels like cats and dogs with their associated images, or it could be something more complex. It doesn't have to be just images. It doesn't have to be just labels on the output. It could be almost any sort of data structure that you can come up with at the input, and almost any other sort of data structure you can come up with on the output. And we'll talk a little bit about some of those applications later. Unsupervised machine learning is the second type. In this type, we don't know what the true outputs should be based on our problem. Instead, we allow the algorithm to adapt to try to find its own patterns within our input data. Because we don't have the same level of control as the previous example, our outputs might not be something we expect, but there's still going to be some sort of pattern that's pulled out from the data. In this case, the yellow, blue, and green represent the background average pixel values that might be in our image. They may not associate to our true problem, which is cats or dogs. And we don't have the same feedback loop that we do because as in supervised machine learning, because we don't know what the true outputs should be for our problem. But this unsupervised machine learning can be a stepping stone onto another solution as we gather those labels, those known outputs. Reinforcement learning is the third type. In reinforcement learning, it's very similar to supervised machine learning. The difference is instead of having a large data set with inputs and outputs, we instead look at examples one at a time. What's shown here is a single example of a cat. It runs its course through the algorithm. It predicts a label. Perhaps it's cat, or perhaps it's something else, an incorrect label. And we get this, we have the known value held in reserve. In this case, we know what the true label should be, which is cat. And we evaluate with this learning feedback, just as in supervised machine learning. Reinforcement learning, because it's looking at one instance at a time, it's often related to time series analysis, where perhaps you're in one state and you're transitioning from state to state. This is used a lot in robotics, where a robotic navigation system or an autonomous driving application, they might be looking at a single example, and then they score themselves as they go with learning feedback. Perhaps it's a driver in the loop telling the autonomous vehicle when it's doing good or when it's doing bad, but that learning feedback is really critical. And often, reinforcement learning is used when there's some sort of simulation or known state to the system. That known state is really important because that's what gives you your feedback in terms of scoring. But how does it all work? I'm going to talk at a high level how machine learning works. We're not going to talk about the code or the math that underlies it, but just some conceptual understanding. So think line fitting. We've all been in Excel, tried to do a line fit to some sort of data points. This is sort of a regression problem where we're trying to find a trend in some sort of data. What this allows you to do is for a new X value that comes in, it will predict a Y value which meets this sort of function. We can extend this to other problems. In this case, instead of trying to fit a line, we're actually trying to separate two different classes. They might be cats and dogs, like in our previous example, but we're trying to find the mathematical function which will, more often than not, allow us to correctly predict cats or dogs when a new data point comes in. For a new data point that comes in, this would allow us to assign a label, either cat or dog, to some sort of unknown input and allow us to calculate an output. If you take a look at the plot, you'll see that some of the data points which lie close to our decision boundary, we're not correctly classifying those. If we had additional inputs or perhaps a more complex decision boundary, we might be able to classify those correctly. Our decision boundary has certain constraints which affect how complex this decision line can be. If we allow the decision line to be more complex, it might fit all these data points, but perhaps when new data points come in, they may not be correctly classified. And it just goes to show that machine learning, it can fit your data, but it may not generalize perfectly to new examples. So we saw some data points on some of the previous slides related to the X and Y axis. But what about for image data? Well, for that one, we're going to take a look at my dog Nasus here. For any sort of machine learning problem, you need numeric inputs and numeric outputs. So for an image, each one of the little pixels in the image represents some sort of numeric value. And that's what we're going to use as our numeric input. For an output, if it's going to be cats or dogs, we might assign a numeric value to those outputs to try to calculate whether it should be 1 or 2. Convolutional neural networks are really the prime example of how to best use machine learning for image data. We're going to try to find some sort of statistical function learned from a large set of data. Just like line fitting, we're going to take a large set of data points, images in this case, and we're going to find some sort of statistical pattern which will allow us to either classify cats or dogs. So many examples of these animals can be used, and these sort of statistics can generate patterns which form the most probable shapes of different characteristics of those images, let's say. So these small patterns, they might be things like the shape of an animal's head, or in this case, it's exaggerated, but the ears of a dog, or the legs and paws. These are statistics which can be pulled from lots of images which represent distinguishing features perhaps that separate cats from dogs. So these small patterns, they can be matched to new examples. And if we get a close match, that could mean that there's a strong correlation with perhaps one of our classes of interest, whether it be cats or dogs. Many combinations of these patterns can be learned and layered, and that's really the foundations of convolutional neural networks. It's about adding additional complexity, and it allows you to learn patterns of patterns, not really something that a human needs to define what they are, but just statistics that are learned from your data set. So we talked a little bit about the technical details which underlie machine learning, but how do you actually apply this to real world problems? How do you use it successfully? Well, it's really about identifying the problem. On my data science team, we have 4 criteria which really enable machine learning success on a problem. Those are having a specific use case, having a performance metric, which allows you to score and provide a feedback path. Third is a baseline solution, something that's not machine learning, but will allow you to score and evaluate the performance of your entire system against some sort of known benchmark. And finally, having a data set, preferably labeled according to your specific use case, having all the inputs and outputs that represent the challenges of your problem. So let's dive into ML use case identification. Many would consider this to be the most challenging step on being successful with machine learning. It's all about identifying what are going to be your data inputs and your data outputs. So what are some numeric values that you can take in as input, and what are the numeric outputs that you want to try to predict? Can you actually collect those inputs and output pairs right now, which would allow you to then build a machine learning solution? For many problems, if you don't know what the true output should be, or you can't collect the data, then that's a huge problem. Ask yourself, can you collect these inputs and outputs at the same time, which allows you to build a data set? Or do you already have this data? And finally, can you match your problem to one of the prominent machine learning setups that are used ubiquitously? These all have pretty standard inputs like images, audio, video. The outputs can be tailored to your specific application. Machine learning use case identification is often one of the hardest steps for being successful. If you have data, sure, you can develop a machine learning predictor, but it may not exactly fit to your problem, or you may not have collected the right data or set up the problem in the right way, which would allow you to be successful. So the second step here, we're going to talk about in detail, is this feedback metric. What is it that the machine learning algorithm uses to score itself, which will allow it to get better over time after it looks at more data? You're going to ask yourself, how can what I want my system to calculate be compared back to some known outputs? What are those numeric outputs? How are those scores going to compare, and how can I evaluate how well I'm doing in my prediction? How are the outputs going to compare to your known outputs? How do you score what your machine learning system produces in terms of its output with the known outputs that you've collected for your data set? When you do score yourself on those predicted outputs and the known outputs, what are all the possible scores that could come out of that? And are they constrained to a limited range? We can't have numeric values that approach infinity. They must be represented discretely in a numeric value. Ideally, you would like to constrain those to a certain range, perhaps a percentile range or small decimal values. We can't have things like zeros and infinities messing up the math. So we really need to box in what these data values can be by constraining them. Besides the math, you just got to ask yourself, does this feedback metric actually solve my problem? If the machine learning algorithm you're developing classifies between cats and dogs, but then you take this thing to a zoo and you ask it to look at all sorts of animals, it's going to give you very unexpected outputs because it's looking at things that it was never intended to look at. For this reason, this feedback metric and the use case identification that it preceded it, you have to be very specific in the way you set up these problems. Finally, it's very important to ask yourself, of all the inputs that are coming into my system, whether it be images or other sorts of data fields, is there enough information there to accurately classify and predict my output? If we're only giving it pictures of cats and dogs and we're asking it to predict the weight of the animal, there may not be enough information in the image to solve that problem. It might give you a very rough estimate but it won't be a perfect solution. Machine learning is not magic. It's not going to give you an output, a prediction, which doesn't correlate back to the input. If there's not enough data in that input to predict your output, um, you don't know what's going to come out of that system. This feedback metric is then very important because it allows you to evaluate the system. You'll be able to identify whether or not there's enough information contained in your inputs which correlate to your outputs. This scoring method allows you to do that. Third, let's talk about baseline performance. I want to stress this heavily. Machine learning cannot solve an unsolved problem. Because supervised machine learning and reinforcement learning are both dependent upon knowing what the output will be, the true value of your output, what it should be, you already have to have some sort of solution which gets you that output beforehand. So machine learning is not going to solve something where you have no idea what the output should be. So you got to ask yourself, what solution currently exists which solves this problem? For many, when we're looking at images, let's say, the human eye interprets those images very well. And so that can be the baseline solution. A human looks at examples of cats and dogs and tries to make that prediction. In this way, you're collecting your output data that you need for your problem because you have that baseline solution. You might also apply some sort of existing algorithm to the problem. Perhaps you have some sort of other computer vision algorithm which classifies cats from dogs. You can apply that as well and score it as a whole to see how well you're doing. That gives you some sort of benchmark performance to meet when it comes to machine learning. Machine learning does a really good job at taking those inputs and outputs and finding a function which goes from A to B. In that way, if your baseline solution or your data has errors in it where you're not 100% sure on what the true output should be, those errors are going to be transferred into your machine learning model. And that's where things could go wrong. If you're pulling data directly from your baseline solution, you're almost certainly not going to do better than that baseline solution. You have to have an additional level of scrutiny on those data examples in order to improve your machine learning model. We talked about where different baselines might come from, but the ultimate goal is to actually take that baseline, a score to evaluate an existing solution in terms of its performance. Usually something like accuracy, if you're trying to categorize between things like cats and dogs. The prediction accuracy can be scored against a data set of known labels. A baseline could also be some sort of other performance measure, like something related to speed or computational performance. Again, the goal is to score the baseline solution so that you have a finish line for your machine learning algorithm. If your ML algorithm can show improved performance over that baseline, you've proven your system. If you don't have a baseline solution score and you approach a very hard problem with ML, you don't know what is within the realm of possible. It could be the problem is simply too hard or there's not enough data to completely solve your problem with ML. Without a baseline score, you may struggle developing a solution for a problem which has no solution. The baseline score allows you to show ML is adding something and is worth investing in. At the end of the day, it must show that ML is improving your system. And a comparison to a baseline score is how you do that. Finally, machine learning labeled data set. So we've talked about specific use cases, metrics which evaluate your A to B, and also the baseline solution that goes from A to B. Now we got to put it all together into a data set, collect a lot of data which will solve our problem. For a supervised machine learning example, you got to ask yourself, what data do I already have? It might be just inputs, but we don't have the outputs. Again, ask yourself, does my data set fit my use case? But you only give it pictures of dogs and you don't have enough cats. How's it going to be able to predict that cat example? if we do have to label data, how expensive is it to do that? For some examples of machine learning, it might require thousands or even millions of labeled examples. Is a human going to go by and label millions of images of cats and dogs? That can take a very long time and be very expensive. Does some sort of other baseline solution exist? Is there another algorithm that you can apply to your data, which will give you a rough guess on your output labels? That could be a good stepping stone to improve your data quality. And then finally, the question that you're really trying to answer here is how many pairs of inputs and outputs currently exist, and how many are needed to solve your problem. It's really hard to know before you get started, but that's where some of the expertise provided by machine learning engineers comes in. So I promised I'd talk a little bit about something other than machine learning. So I'm going to offer a little bit of my perspective when it comes to race in America in the military. If we choose to ignore contributing factors, it's really hard to see statistical correlations in our data. Just as humans are biased, data and the associated labels can also be biased. In that same way, machine learning algorithms can be biased towards particular points of view. Whether we're talking about racial equality in America or just machine learning in general, it's important to analyze and identify different perspectives. Our machine learning systems will have the same viewpoint as those that labeled the data examples. It's important for machine learning engineers to view different sides of the story in order to identify different perspectives that may apply when these are applied to the real world. This is where things get a little tough, and I'm going to keep it real here. Being brown skinned in America is not easy, as I'm sure many of my fellowship members here can attest to. When I was growing up, I had a lot of problems being misunderstood by my peers in school. I was the odd one out, picked last for sports, not many friends. I didn't fit in with the US majority. Why? I didn't realize at the time how big a factor skin color had affected my early social interactions. Whether it was in school or elsewhere, that someone who doesn't know me already has a preconceived view. When I'm walking down the street, I get glares from people, passersby, overt reactions of fear. And you just know that they don't trust you based on your skin color, and it hurts. There is an all too common perspective among the American public that dark skin colored people are dangerous. We all have unconscious biases, and we can't always control our basic reactions to fear. But what really upsets me is when people can't comprehend the racial bias in what they say. Sometimes I get very pointed questions like, where are you from? But what the person really wants to say is, I just know someone who looks like you can't be from the United States. Call it a microaggression, call it whatever you want. I look them dead in the eye and I say, I'm from here. I'm from Arizona. My ancestors were here before it was a United States territory. Certainly before you were. Where are you from? Or at the very least, I'm going to confront racism when I see it, since so much of racial bias is hidden. You can't help people's perceptions when they first meet you, but you can leave an impression after they do. When I was in school growing up, in middle school is when the September 11th attacks happened. The color of my skin suddenly became a huge factor. I was ridiculed even by my closest friends on the color of my skin as being something other than the norm. Being called a terrorist based on the color of your skin is something that I'll never forget. I had to prove that I was as American as anyone else that lives in this country. And that really started me down the path of military service. Many of my earliest role models had some sort of military service in their past. My football coach, my neighbor down the street, all of my uncles and my father, where I had found a lot of misunderstanding amongst the general United States public, I found acceptance in the United States military. It didn't matter what the color of your skin was. Suddenly, I was a part of a brotherhood which all shared a common goal. I was born anew into a new perspective. I told myself that my skin color is not brown anymore. It's military green. For years, I've told myself that skin color was not a factor for me anymore. But with the current state of the United States, I've had to reevaluate my own personal views. I can no longer deny how race, culture, and skin color affect my personal and other people's experiences here in the United States. As a fitting example, I've always struggled with this question on standardized tests on the United States Census. What race am I, America? There's no checkbox for brown skin color of South and Central American descent, even at this fundamental level where we try to identify for demographics. There's no checkbox for anyone who comes from descent from south of the border. As an example here, you see where many people trace their lineage back to. It's a more thorough representation, not simply skin color, white, black, but this looks at a little bit more fine detail. When you split up the Caucasian white American majority into the different subgroups which comprise it, whether it be English descent, German descent, French, or Scandinavian, or other, you suddenly get more perspective on how many people trace their heritage back to Mexico. Along the southwest border of the United States, you'll see that there's more people that trace their heritage back to Mexico than any other country of origin. This is in sharp contrast to the demographic surveys, which don't even consider people of brown skin. It takes a whole separate question on the demographic survey, whether or not you have Hispanic descent, but it doesn't address the issue of brown skin color. Another thing to note here is many of even the Caucasian ethnic groups here on this chart face some sort of discrimination over the course of America's history, whether it be Germans during the past world wars, or Irish, or Italian. All these ethnic groups in the past were discriminated against. It wasn't just because of the color of their skin, but simply their heritage. Discrimination against somebody, anybody, really runs deep in America's history. And it takes an active aversion to it to try to overcome that for future generations. We talked about how race has and still does affect America. Another important contributing factor is safety. It's important to put the safety that we enjoy as Americans in the 21st century into perspective. The 20th century was marked with the largest wars in the history of mankind. Millions of people perished in the two world wars of the previous century. The Vietnam War, whether you support it or not, 10% of that American generation deployed into a combat zone. During the peak of the Cold War, there was over 60,000 nuclear weapons ready to launch. Any one of those could have destroyed an entire US city. Everyone in the United States, the baby boomer generation, lived in constant fear of the atomic bomb. Regardless of whether our involvement in these wars is just or not, the United States military deployed to war to defend America's interests. In the last century, over 400,000 soldiers, sailors, Marines, service members gave their life in support of the United States. By contrast, since the year 2000, we've been at war for almost 20 years in the Middle East, but a total of 5.6 thousand service members have given their life in combat. Advances in technology have greatly reduced the terrible human cost of war. Additionally, where previously 10% of the American generation had deployed to military combat, today less than 1% of the entire US population has ever deployed in support of military operations. The scale of our involvement in military conflicts has greatly reduced, but it's not to say that the world as a whole is a safer place. We as modern Americans should be grateful to live in a land where we do not fear imminent attack by another nation. This has been earned by the sacrifice of so many. But this safety is not guaranteed forever. It pains me to say it, but the sacrifices of my brothers and sisters in the military helps to ensure the safety of us all. Thankfully, fewer and fewer service members are asked to sacrifice on our behalf. Our United States of America, it's not perfect. There is inequality. But our citizens live in relative safety. It's been almost 100 years since we've had to fight a war on our own soil. And it's taken hundreds of years to build the democracy which we enjoy today. The right to free speech, the right to protest, these are cornerstones of our democracy, but many nations do not enjoy these same rights. We've enjoyed over a century as a major world power, and we rose to the world stage through our involvement in war. Technology has given us the advantage in the past and continues to prove vitally important, helping us to strengthen and secure the United States into the future. Now that the stage has been set related to the United States military, we're going to look at the 4 enablers of machine learning success and apply those to a couple different problems. So you guys might have seen this in the news recently. The Alpha Dogfight trials, a DARPA program to develop an artificial intelligence which can fly a jet fighter in a dogfight. The trials recently ended, and the result was a champion AI which beat out an experienced human dogfight pilot. But what are the steps that it took to get to that point? Well, for this particular use case, your inputs might be the current environment of your aircraft's trajectory and the trajectory of your opposing aircraft. The outputs would be the control of your aircraft during that dogfight scenario. This application fits very nicely into a reinforcement learning approach. We provide that feedback metric when we win or when we lose during one of these dogfights. In this way, the machine learning model can get better over time by applying things that it did to win and not doing things which might have resulted in a loss. What sort of baseline solution exists for this problem? Well, we can apply some of the knowledge of experienced pilots in this dogfighting scenario. But does that allow us to collect all the data that we need? Does that allow us to build a vast data set of all the possible scenarios of dogfights? Not just on those experienced pilots, no. But what we can do is create a simulation environment which allows us to train repeatedly over and over again, experimenting with many, many different dogfighting scenarios. With enough time in these simulation environments, the machine learning element can learn everything it needs to adapt to a variety of different scenarios. Only those that were contained in the simulation. Here's a second application for you. Software exploit detection. There was another DARPA Grand Challenge which involved training an AI to find code vulnerabilities. So what are our inputs and outputs in that scenario? Well, the inputs might be lines of code or machine binary. And the outputs would need to be, where are the true vulnerabilities as identified by an expert? The feedback metric could be, how often is an attacking machine learning element able to penetrate into the system? Are you able to have this positive feedback when it correctly identifies a software vulnerability? If you can tell it when it's doing good and when it's doing bad, you can allow it to adapt over time. The baseline solution here is probably going to be some sort of existing tool suite when it comes to identifying software vulnerabilities. The data set here could be some pre-recorded list of many exploits, or it could be this reinforcement learning approach where you train example after example, perhaps looking at many lines of code in sequence. The third example here is a deepfake detection. So in social media, it's a known problem that there's this new and emerging deepfake technology where you can get your favorite actor or president to say and do whatever you want in terms of a silly video. Those can also be very malicious when the ultimate goal of an attacker is to spread misinformation. So this deepfake detection challenge was put on by many of the tech companies, including Google and Facebook, but it has ties to military applications. What are your inputs and outputs here? Well, the inputs might be known examples of deepfake media with the associated label on the output saying this is or is not a deepfake. The feedback metric is simply how you scored that. The baseline solution must have come from some sort of expert which classified it already as deepfake or not. The data sets were generated from social media networks and represent many examples of humans clicking feedback to tell the social media networks that there is some sort of false information here. They then collect those and put those into a data set. This next example is something that is pretty close to home at General Dynamics Mission Systems. Working with the United States Coast Guard, they process many distress calls for sinking ships and emergencies. In many of those cases, there may be extreme examples of background noise, which may limit the interpretability of that Mayday distress call. So setting up those input and output numeric examples. The inputs could be audio examples from distress calls. And instead of a classification output, we can instead generate a new audio sample. It's a complex output, which represents a cleaned version of that audio example. To know both the clean audio output and the obscured audio input really requires some sort of simulation to generate that noise, which allows you to have both the noisy example as the input and the clean example on the output. So what's our feedback metric then? Well, if we ask our machine learning algorithm to generate a segment of audio as an output, we can compare that generated audio back with our ground truth known output, the clean audio. However close we are between those two outputs, that's our score that we use for feedback for improving our machine learning algorithm automatically. The baseline method here is a little bit tricky. We might use some traditional audio filtering techniques and compare those with our machine learning algorithm to generate a baseline performance measure. And finally, as I already said, the data set, that's going to be generated from some sort of simulation because you got to get both the clean audio and the noisy example. And so applying that noise through some sort of simulation, that's how you generate your data. And we've finally gotten to one of the more popular uses of machine learning, and that's for imagery. So overhead imagery might come from a satellite or some sort of drone. We want to detect different objects in that imagery. Our labels, our outputs, those might be boxes like is shown here in the video. They might be different types of cars. Here you can see different colors which represent small or large vehicles. The feedback metric is going to be how close our algorithm is at predicting the size, shape, and location of these bounding boxes. If we're predicting good bounding boxes, we get a good score. If we're not predicting good bounding boxes, we get a negative score. And that feedback allows the algorithm to adapt and improve. As we apply our machine learning algorithm, we'd like to score ourselves against some sort of baseline solution. So that might be some sort of other algorithm. We want to show that we can either do it faster or more reliably than an existing algorithm. And that shows that machine learning is really doing better than some other system. For many of these military applications, the data set really needs to come directly from the source, and many of those data sources are classified. The US military has taken strides to improve how it collects and labels data for use in these machine learning algorithms. Our final example here is radio signal identification. Our inputs might be digital recordings of radio waveforms, and our outputs might be exactly who's speaking during those radio transmissions, or what they're saying, or some other sort of metadata associated with that transmission. As long as we can record both those inputs and outputs, that allows us to build a data set to approach that problem. Similar to many other classification problems, the feedback metric is going to be how accurately are we able to classify into our labels of interest. A baseline solution might be some sort of subject matter expert analyzing the same waveforms and coming to their own conclusions. We'd like to score them as well to show that we're either able to do it better or faster than some sort of existing baseline. Finally, the data set, because we need to know both the input and output, we either need to have a human label many data examples or create a simulation environment to generate data. Artificial intelligence is being used in the military more than ever. It's our responsibility as engineers to apply ethical guidelines towards those applications. There's life and death consequences at stake. The US Department of Defense has recently released its ethical guidelines for using AI. At a high level, there's 5 key elements which the Department of Defense is pushing. The first key point here is responsible. For applications that may use AI or machine learning, there should be a human that is included to make responsible judgments so that there is not only a software algorithm making decisions. An equitable AI, as we discussed previously, would try to root out unintended bias, which may negatively affect a machine learning algorithm. Traceability is important to show all the considerations during the design and development of an artificial intelligence or machine learning algorithm. Reliability testing has always been very important in the military. It is especially so for machine learning applications which rely on data examples. If we do not test these thoroughly, machine learning algorithms may deliver unintended results. It is governable in the sense that it is only operating within the rules of its design. An algorithm should be able to identify when it is operating within its intended scope. When it exceeds that scope, it should be able to turn itself off to disengage in order to avoid unintended behavior. We've nearly reached the end of the presentation here. Some future considerations for artificial intelligence and machine learning. They are advancing rapidly within the Department of Defense. Data collection and labeling to get those outputs are a big priority for the military. For some specific machine learning use cases, they are showing considerable success over traditional AI methods. Oftentimes, computing power is still a limiting factor. If we can apply a cloud server to applications, oftentimes these generate good results, but we're limited by the amount of compute power within small electronics that may exist on a battlefield. And finally, general purpose AI is still a long ways off. We're only able to solve problems with inputs and outputs, this A to B relationship. For anything outside that scope, a machine learning algorithm isn't going to be the solution. You don't have to worry about an AI gaining self-consciousness. We're really a far ways off from that. It's only these small, simple, specific problems which we found success on. I'd like to end with this. Si vis pacem, para bellum. If you want peace, prepare for war. In the 21st century, war has become less common, but conflicts between people is inevitable. It's impossible to predict the future, but certainly limited resources in this world will always cause conflict. Despite this, we should prevent war whenever possible. Diplomacy should be our first tool, but having a strong military to back up our words is important. Human life is our most valuable resource, whether it be the citizens of our country, our military, or the citizens of this world. That's why I work for General Dynamics Mission Systems. I believe my actions are making an impact on the future, creating a safer world for all of us. Just a quick shout out to my team. I work for Deep Learning Analytics, part of General Dynamics Mission Systems. It's a small team of data scientists working on some pretty hard problems for the military. If you are an aspiring data scientist, come check us out. Thank you for attending my presentation, and I hope you enjoy the rest of the ShipConf.